single bonds instead, like here in ammonia, 3 single bonds. And the same thing for oxygen. We don't need to do an oxygen double bond. We could do single bonds to the oxygen as well. So we'll get to the octet. And then we have some odd species here. These odd species I'll probably talk more about later. But there are some species that, if you look, does nitrogen have an octet here? No. Nitrogen has 2, 4, 6, 7 electrons, one short of an octet. Oxygen has an octet. That's 2, 4, 6, 8. So we have the octet. And so this is less than an octet. That less than an octet makes this pretty unstable. And this is nitrogen monoxide. Nitrogen monoxide is what we call a free radical. Free radicals have this kind of dangling electron here. So it's not that. Nitrogen dioxide is also a free radical. Whenever we have an odd number of electrons here, like in this species or in this species, we're going to get a free radical generated. That's less than an octet. Down here we see some species with actually more than an octet. You know, phosphorus. Did I talk about this yet? No. If we look at phosphorus, phosphorus has 2, 4, 6, 8, 10 electrons. So it's 2 more than an octet. And this sulfur is even worse. So it's 2, 4, 6, 8, 10, 12. And so these are called expanded octets. And why would you have more than an octet? The reason you have more than an octet is, well, it doesn't seem right, because if you have more than an octet, it's got to go into the next higher energy orbitals. Going into the next higher shell is unstable, but there's something stabilizing it, and that something is forming additional bonds. And so the more bonds you form, the more stable it is. And so here we've maximized the amount of bonding there, 6 bonds. Here we got 5 bonds as well, which is a max for phosphorus. And so sometimes you see species that violate this octet. Here's a couple that have less. This is beryllium difluoride, which forms a molecular compound. This is boron trifluoride. This is also a molecular compound. Boron trifluoride is less than an octet. The same thing with this. Boron trifluoride is pretty reactive, though. It wants that octet. And the one way of getting that octet is to react with what we call electron pair donors, which makes boron trifluoride an electron pair acceptor, and that's what we call Lewis acid. So boron trifluoride is a good Lewis acid. But we'll talk about these species later. Okay, that's covalent bonds. We'll have single bonds, double bonds, and triple bonds, and then we have these odd species like this. And then we have metallic bonds as well. Metallic bonds are the bonds that hold metal atoms together. And typically, when people think about metal atoms, they think about, did I talk about this electron C model? No? They talk about the electron C model. The ocean would be like the electrons here. The electrons in a metal are free to move anywhere they want. And so we call them an ocean or sea of electrons. These are what we call delocalized electrons. And the way we think about metals, let's skip for right now, but the way we think about metals is like this. Metals have very loosely held electrons. And those electrons aren't held tightly to any particular atom. They just kind of move around like the ocean. However, the atoms are fixed, like pure ions in the ocean. So this would be like sodium. And so the bulk, the core and the electrons and the nucleus form this ball here, and the net charge is positive. The valence electron's out here. The valence electron free. So sodium metal would be like this. The atoms are fixed. They'll vibrate, but they're fixed. The electrons are delocalized, but they're free to move. They're loosely held. This would be magnesium. You know, magnesium would have nucleus and core electrons here, which gives it a net 2 positive charge, and then the valence electrons out here, and the valence electrons are mobile, free to move. This is called a metallic bond, and one way of visualizing it is electron C, or delocalized electron model. This is what they call the electron C. Oops. Here. Electron C. All right, the thing about the metals is you can substitute some atoms. So let's pull one atom and substitute something else. So if that's sodium, we can put a potassium in there or put a lithium in there. Those are called alloys. Alloys are just mixtures. These are very homogeneous mixtures because what we can do with the structure is like this. We'll remove the sodium and put a potassium in there. Now, alloys can have variable composition, and so they aren't compounds. Compounds would have fixed composition, so it depends on how many sodiums I remove and how many potassiums I put in its place. It can have varying degrees or varying compositions of potassium in there. And so that's what we're going to see for alloys here. And let's take a look at some common alloys, like 18 karat gold, 75% gold, 12.5% silver, and 12.5% copper. So we'll be taking some of the atoms out and substituting other atoms in. But it's not fixed. I mean, well, 18 karat is supposed to be a fixed composition. You know, if you buy 18 karat gold, it should be 75% gold. But is that really fixed by anything? It's like water. When you buy water, it's going to be 11% hydrogen, 89% oxygen, always, right? But if you buy 18 karat gold, is it always going to be exactly 75%? It should be, because you're paying a lot of money for it, but there's going to be small variations in it, you know, depending on who manufactured it. There should only be one composition of 18 karat gold, and that has to be mixed and certified. However, brass, there are many. I think there are over 1,000 different brass compositions. So just with different degrees of copper and zinc, you can mix those in any proportion. Bronze, 90% copper, 10% tin. Steel, 99% iron, some carbon, some other stuff. Pewter is mostly tin, some antimony, copper. Stainless steel is 70% iron, some chromium and nickel. Chromium and nickel give it some resistance to corrosion. So stainless steel is much better as far as quality goes than plain steel, carbon steel. Sterling silver, 92.5%. But none of those compositions are really fixed, like water, you know, or sodium chloride, or whatever else. You know, these all have variable composition. And so alloys are just physical mixtures of metals. All right, we're going to continue this in chapter 13. So in chapter 13, we're going to look at structures and shape of these. So let's start here. The first thing is we're going to draw the structure of these, the bonding arrangement. And typically, when we draw this structure, we're going to draw the Lewis structure. So we already saw some Lewis structures. We saw Lewis structure for ionic compound, and we saw Lewis structures for molecular compound. And so let's draw the Lewis structure for ammonia. There are different ways we could draw the Lewis structure for ammonia. You know, one of the easiest ways of drawing the Lewis structure for ammonia is by drawing out the Lewis symbols. If we look at ammonia, excuse me, the Lewis symbol for nitrogen has how many dots around it? Five. 5 valence electrons, 5 dots. And then hydrogen has 1 dot. And so how many electrons does nitrogen want? Nitrogen wants 3 to complete its octet. And so it's going to attack those hydrogens. And so one way is we can just go ahead and put the pieces together like this. You know, let's see how the pieces fit together. The pieces are going to fit together like this, so we'll end up with 3 hydrogens coming in to form a covalent bond with nitrogen, like that. And so we can have the pieces here and then build it from there. And so we can do that for a lot of species, but some species are a bit more complicated, and we need a more general procedure for doing it. So for example, if the nitrogen has a positive charge rather than neutral, this is neutral nitrogen. So nitrogen might have a positive 1 charge. If it has a positive 1 charge, how many electrons does it have? Or it has a negative charge, how many electrons does it have? You know, if this nitrogen has a positive charge, then it's missing 1 electron, so it would have 4 dots. If this nitrogen had a -1 charge, it would have an extra electron and 6 dots. But we don't want to keep track of all those, although we could, and build molecules that way. What we're going to do is we're going to follow step-by-step procedure. The step-by-step procedure, when we're trying to draw a Lewis structure, this is going to be for Lewis structures for molecular compounds and ions. When drawing the Lewis diagram, or a Lewis structure, count the total number of valence electrons, adjust for charge, place the least electronegative atom in the center of the molecule, draw the tentative diagram joining atoms by single bonds, add unshared pairs, to complete the octet around all atoms except hydrogen. We'll get practice using these steps, so after you use them a bunch of times, then you kind of know what to do without having to consult it. Step 4, calculate number of valence electrons in tentative diagram and compare with actual. If diagram has more, remove lone pair from the central and terminal atoms and replace with additional bonding pair. Repeat process till the numbers match. Check the Lewis diagram. Hydrogen atom must have only 1 bond and all other atoms should have a total of 4 electron pairs. That's not exact. Step 5, there's exceptions to step 5, so I don't really look at the rules too much. So let's use the rules to make ammonia, or the steps, rather than this, putting together the Lego pieces type approach. And so step 1, we need to total up the number of electrons. So let's see how they did it. The valence electrons. So here, what are they doing here? So they've got 5 parentheses n plus 3 times 1 parentheses h equals 8. Where does that come from? Where does the 5 come from? Yeah, 5 is the number of valence electrons for nitrogen. 5 from nitrogen, and then each hydrogen has how many valence electrons? 1, and we have 3 hydrogens. So it's 5 plus 3, which gives us 8 valence electrons. And then we should put the least electronegative element in the center. Which one's more electronegative, nitrogen or hydrogen? Did I talk about electronegativity yesterday? Yeah. What's the most electronegative? Fluorine. So nitrogen is much closer to fluorine. Therefore, nitrogen is more electronegative. And so hydrogen should go in the center, but there's one problem. Hydrogen is never in the center. Hydrogen's always on the edges. We call hydrogen a terminal atom because hydrogen doesn't like to form more than 1 bond. Hydrogen prefers just 1 bond. And so in this case, we're going to have to put nitrogen in the center. So we have no choice. Even though the nitrogen is more electronegative, nitrogen can form more bonds. So let's just throw it in the center. And so how many electrons have we used so far? We've used 2, 4, 6. And now what we need to do is we need to complete the octet. But does hydrogen get an octet? No, hydrogen gets a duet. And so hydrogen is good. This hydrogen is good with 2 electrons. It only has to fill the first shell. The first shell, its maximum capacity is 2 electrons. So we got filled first shell, filled first shell, filled first shell. But nitrogen has to fill the second shell, which needs 8 electrons. And so you can see nitrogen is going to come out short. 2, 4, 6. Each line represents 2 electrons. Right? But how many electrons do we have in this structure? We have 8 electrons, so we have 2 extra electrons. Now, the 2 extra electrons typically go on the terminal atoms. The terminal atoms would be these versus the central atom. And so first we try to complete the octets or duets on the terminal. Those are all complete. Then we'll put it on the central. And so we end up with that. This would be the structure for ammonia, NH3. Okay, this would be following the rules here. Okay, what they say is since a hydrogen atom is never central, the nitrogen atom must be central. Okay. And that's the structure they got. 8 electrons in the tentative diagram match the number available. The diagram is complete. Well, not exactly completely. We do some extra steps here. We have to do some extra steps because some molecules are a bit more complicated than this. So for simple molecules, we're done. What are these extra steps? Well, the extra steps are related to sometimes we can draw different structures for the same molecule. sometimes we have to figure out which one should be the most stable. But anyway, this is the correct structure for ammonia. What are some properties of ammonia? Okay, NH3. This is just review some properties. One of the properties of ammonia is it a solid, liquid, or gas? You know? This is ammonia. A pure ammonia is a gas. How did I know? I had it memorized. No. Ammonia is a gas. So that means its boiling point must be fairly low. I mean, if it's a gas, it's got to boil at temperature less than room temperature. It's a colorless gas. No. Has a very distinctive odor to it. Those are some physical properties. But tell me about some chemical properties for ammonia. If I'm interested in the chemical properties, physical, yeah, gas, colorless, odor. How about the chemical properties? What do we look for in chemical properties? Tell me some chemical properties for ammonia. Well, one thing, you know, probably when I first started chemistry, you probably take some ammonia and start mixing it with a whole bunch of different chemicals and seeing what happens, you know, see what happens, what reacts. So you take a look at what's on the shelf and then start mixing, seeing, but, you know, that would take a lot of time. And then once you do that, you can memorize, you know, all the things that reacted with ammonia, or write it down. So you can consult it later, but we don't want to do that. Should be a better way to figure it out. And so what chemical properties are there? You know, what are the main types of chemical properties? There's metathesis. Okay, let's stop there. What do you expect from metathesis?
Ion.
Yeah, and so what kind of metathesis reactions would ammonia undergo?
Can it react with water?
It can react with water, yeah. Is that a metathesis reaction? Well, one thing is, ammonia is, I wouldn't think, ammonia is molecular. Ammonia is molecular. Ammonia isn't an ion, or it doesn't consist of ions. And so, since ammonia is molecular, we don't expect any metathesis reaction. We don't expect metathesis reaction to occur directly with ammonia. But it doesn't occur directly with ammonia, it occurs indirectly. Because what happens is an acid-base reaction can occur. And so this acid-base reaction with water, this is a Bronsted acid-base reaction, is going to form a little bit of what? Ammonium and hydroxide. So we get a little bit of ammonium and hydroxide. Well, not much, but enough so that we could see metathesis. Now, metathesis isn't going to occur with ammonia, but metathesis will occur with these. And so these will have metathesis properties. And so let's start off with ammonium first. We generate a little bit of ammonium through the reaction of ammonia and water. And the ammonium can react with what? Well, metathesis is, well, what is metathesis? You know, metathesis is
Favorable ion combination.
favorable ion combinations. So what ions does ammonium like? So what do we think? Okay, what anions will ammonium precipitate with? Any?
No.
No. It's soluble and all. So there's not much happening with metathesis, is there? No, not much. There are some ions that ammonium likes, but those ions could also be classified as bases, you know. And so these are some ions ammonium likes. Here's ammonium. Will ammonia and ammonium react? No. If ammonia and ammonium react, we get ammonium and ammonia. So we end up with the same thing, which means that there's essentially no reaction, no net reaction. Well, yeah. And so, do we need a stronger base than ammonia or a weaker base than ammonia? We need a stronger. So ammonium likes cyanide ions. Ammonium likes carbonate ions. Ammonium likes phosphate ions. And so ammonium likes these ions, ions that are stronger bases than ammonia. So that's then it'll react. How about hydroxide? Well, hydroxide likes all cations except for group 1, ammonium, and hydroxide likes all cations except for group 1, ammonium, and calcium, strontium, and barium. Why? Because it'll precipitate. You know, it'll precipitate with things like iron ions, copper ions, zinc ions, precipitate out with most, except for group 1, ammonium, and calcium, strontium, barium. It reacts with all the others. So just pick a cation and see if it reacts. And so there is some metathesis, but the metathesis is the secondary effect from the initial acid-base reaction. So we generate a small amount of ions which can react. So that's metathesis. After metathesis, we look for what types of chemical properties? Acid-base. Well, here we have the acid-base chart. Here. Now, we were talking about ammonium earlier, but the ammonium was generated when ammonia reacts with water. You know, ammonia, what would we classify ammonia as? Looks like ammonia is a decent base. So, but ammonia is a bit strange because if we scroll down this chart more, we also see that it's an acid. And so ammonia is what we call amphoteric. It's both an acid and a base. But it definitely has a bias. It's biased towards base or biased towards acid. Base. In fact, the acid, where you look here, you know, these acids are so bad, we don't really even consider them acidic. Like hydroxide, you know, hydroxide. And so basically the acid is so bad that we typically think of ammonia as a weak base. It's one of the stronger weak bases, but still it's a weak base because it's on the weak base end of the spectrum. That being the case, ammonia will need to react with acids that are stronger than ammonium or weaker than ammonium. Yeah, and so any acid stronger than ammonium, is HCN stronger than ammonium or weaker than ammonium? Weaker. So it's not going to react with HCN, but it should react with H2PO4 minus, H2S, etc. And so all those. And so here we could figure out what ammonia reacts with in an acid-base sense. If we treat ammonia as an acid, then we need a base that's stronger than. You know what this base is called? NH2 minus? Amide. Good. Amide. A-M-I-D-E. Hey, if we use that chart over there, do you know what the strongest base on that chart in the back of the room is? it's amide. The strongest base on that chart is amide. Is there any base stronger than amide on that chart? No. So if we're using that chart, then we're out of luck because there's no base that's going to be strong enough to react with ammonia. But this one is has a little bit more on the base end of this. And so what bases will ammonia react with, the acid ammonia react with? Well, the acid ammonia is only going to react with the most powerful bases. And what are the most powerful bases? Are the bases more powerful than amide? Yes. What are they? This is not peroxide. This is oxide. Peroxides. This is oxide. This is called hydride. Hydrogen monatomic is hydride. And this is called, this one's called methide. M-E-T-H-I-D-E, methide. From methane. Forms methide. Those oxide, hydride, and methide are extremely powerful bases, way more powerful than hydroxide. And so those are pretty much the only things that will attack ammonia, force ammonia to give up a hydrogen. Otherwise, ammonia attacks other species. Here. And so that's the acid-base properties of ammonia. And then after the acid-base properties, what do we look at? So we check metathesis, acid-base, and then redox. Look at redox. Do you see ammonia on our redox chart? Ammonia doesn't occur on a redox chart, which means one of two things. One, the redox properties of ammonia are insignificant. Or two, it just was one of those sacrifices they had to make. There was not enough around. But redox properties are significant. And so what do you think it is? Ammonia doesn't have any significant redox properties, or ammonia does have significant redox properties? They just omitted them from this chart. Yeah, exactly. It does have significant. Have you heard that saying, do not mix bleach with ammonia? Why? Because you can generate toxic gases potentially, because ammonia is, well, bleach we know is bleach an oxidizer or reducer? You know what bleach is? Is bleach an oxidizer or reducer? Well, bleach is not on this chart either. Well, the thing is, I'm asking you is bleach electron rich or electron poor? Or ammonia, is ammonia electron rich or electron poor? Because oxidizers are electron poor, reducers are electron rich. And so we can just go on the side here and then look at bleach. Bleach is, you know what bleach is? Bleach is this. What is this called? NaOCl. It's bleach. The active ingredient in bleach. This is like a 5% mixture. The name? Okay, how about if I wrote it like this? NaClO. Name? Sodium, what? Chlorine oxide? No.
Sodium hypochlorite.
Sodium hypochlorite, yes. This is sodium hypochlorite.
Why did they write that?
It doesn't matter which way you write it, that way or this way. I wrote it this way because we're used to ClO, ClO2, ClO3, ClO4, minus, 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 minus. And here's our series: hypochlorite, chlorite, chlorate, perchlorate. And so this is hypochlorite electron poor? Sodium ions, are sodium ions reactive in redox reactions? No, they're stable. Sodium metal, unstable. Sodium metal is a great reducer. Sodium ions, awful as far as oxidizers go. That's because of the conjugate relationship. You know, if one side is very strong, the other side is very weak. But going to ClO minus, what do you think? Electron rich or electron poor?
Rich.
Electron rich has got a negative charge, so it's electron rich, right? That's the case. No, we actually, it's not the case, because when we're looking at electron rich and electron poor, we don't look at the what we call the net charge. We look at the individual charges of the individual atoms. And so what are the charges on the individual atoms? What's the charge on oxygen? The charge on oxygen is -2. That means the charge on chlorine is +1. Oxygen's happy as is. Oxygen is very happy at -2. In fact, in water, we see oxygen at -2, and water is very stable. It's not electron rich. No. If water were electron rich, then you should be able to burn the stuff. Does water burn very easily? No, not at all. How about chlorine? Is chlorine pretty happy at +1? Yeah? No? No. Chlorine's very unhappy because chlorine wants to be -1, not +1. It's quite unhappy. And so bleach is an oxidizer. And so what is ammonia? Ammonia must be a reducer. And so ammonia is electron rich, but it's neutral. Why is it electron rich? Can you tell me? Because of the nitrogen. Yeah. What's the hydrogen's charge? +1. We have 3 of those. And therefore nitrogen must be -3. So -2 is fine for oxygen. -3, you know, that's what nitrogen wants, but it's hard to hold on. It's got too many electrons, even though it wants that octet, a little bit harder to hold on. So it's susceptible to attack. Yes, it wants 3 to complete its octet, but we consider this electron rich. Even though oxygen at -2, we wouldn't consider it electron rich. And so, you know, the numbers are relative to what the atom is. And so if you mix bleach, an oxidizer, with ammonia, a reducer, you might form what might you form? You might form oxides of nitrogen, amongst other things. There's this chlorine there as well. Things like NO. NO is not that happy, you know, actually. NO is not that happy, it's toxic gas. NO2, also a toxic gas. NO2 is a brown gas, NO is a colorless gas. And so both these gases, NO2 is in photochemical smog, it's that brown gas, the brown layer you see in smog. And it's also very, very much an irritant because it's a free radical. You know, it wants another electron. Same thing with NO, it's a free radical, it wants another electron, you know, to complete that octet. And so those are pretty reactive. All right, so that's the redox properties there. And for redox, we look at the oxidation numbers. And oxidation numbers are very useful. Whenever we're thinking about redox properties, we look at the oxidation numbers. So we just did it here, we did it here. But when we're looking at Lewis structures, we don't always look at the oxidation numbers. In fact, when we look at Lewis structures, there are actually four ways to count the electrons in Lewis structures. And so, what are the 4 ways of counting electrons in Lewis structures? So let's take a look at counting electrons. The first way is the octet/duet. And so for something like ammonia, this, then we look at the total number of electrons surrounding that particular atom. So if we look at nitrogen, they're going to be a total of 2, 4, 6, 8. That's an octet. And then if we look at hydrogen, we double count. And so that's 2, that's a duet. This is 2, that's a duet. That's 2, that's a duet. So we double count these. And so we have an octet around nitrogen and a duet around the hydrogens. We're good. That's the octet duet. And then I'm going to talk about the second way we count electrons. The second way we count electrons is the oxidation state or oxidation number. And that's the way we've been counting for redox properties. We've been counting this. But let me tell you what this method of counting is. This method is, just how many are surrounding it. It's okay if we double count. In the following methods, we can't double count things. We can't count it twice. For oxidation state, what it boils down to is this: winner takes all. Takes all what? Takes all electrons. Winner takes all. With a winner takes all scenario is what we call 100% ionic bonding. Winner takes all, that equals 100% ionic bonding. And so this, of course we're just assuming. And so let's take a look at ammonia. Who's the winner? The winner is going to be the more electronegative, the one that's going to pull harder. And so in this case, the winner is going to be nitrogen or hydrogen. Which one is more electronegative? Nitrogen or hydrogen? Nitrogen. Nitrogen has an electronegativity of 3.4, hydrogen is 2.2. And so nitrogen wins all the electrons. That leaves hydrogen with nothing. And so here, what that means is how many electrons does nitrogen end up with? It ends up with 2, 4, 6, 8. Do you remember how many electrons nitrogen contributed to this structure? How many valence electrons did nitrogen contribute? 5. So if it contributes 5 and then it ends up with 8, then it gained 3 extra electrons. If it gains 3 extra electrons, then it gains 3 extra negative charges, and its charge is going to be -3. The hydrogens have lost. And so hydrogens contributed how much? 1, and they end up with none. And so they came out the loser on the losing end. So this is +1, +1, +1. And so with oxidation state is we look at the contribution of each atom, and then we see how the electrons were divided up, and we see if it comes out ahead or behind. In other words, if it came out with extra or came out with a deficit, or if it just broke even. This is one way of thinking about this is this would be like the taxes. California pays taxes to the federal government, and so for every dollar that goes out to the federal government, how many dollars does California get back? Does it break even? So you pay $1 in federal taxes, do you get $1 back? No, actually we come out behind, right? We're at a deficit. We're positive. A deficit. Whereas other states, they pay $1 and they get more than $1 back, right, from the federal government. And so some states come out ahead, some states come out behind. Well, the same thing with Lewis structures. Each atom is going to contribute a certain amount. Some might come out ahead, some might come out behind, some might just break even. So that's what happens here. So this is the way we've been counting. so far, and this counting method is very useful for determining redox properties, but it's not as useful for determining Lewis structures, what we're talking about now. When we're determining Lewis structures, we don't want to look at the oxidation state. We're going to look at formal charge. And so we'll look at, after the break, we'll look at formal charge. So we'll take a break.